Welcome to another lecture. So today we'll look into learning decision trees. So the idea is that given some previous observations, I would like to represent that information in a tree-like structure so that we can answer a, unknown observation. We can answer for an unknown observation. So the idea is that given any past informations, past observation, a set of observation using which you would like to represent a concise structure so that we can answer a query which is not known to query for a particular observation that is not seen earlier. So when you talk about this, first thing we need to look into what do we mean by learning. So this learning is the learning for an agent is required uh, because we want our agent to be intelligent one. And how we can say that the agent is actually learning? If it improves its performance on future tasks after making observation about the real world. So 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 it improves its performance on future tasks. So after looking into a set of observation, it will gradually learn, or it will gradually start predicting it correctly. So now the question is, why would an agent learn? Because because when this agent is built, the designer may not know all possible situations, because there can be unknown situations, or the situation or the set of situation can be pretty large, so which is not feasible for a designer to explicitly enumerate all possible situation. And even designer cannot also anticipate all changes over time, because over the time something can get changed, but we expect that the system will learn all those things and it will adapt itself over the time. And interesting thing, many times the designer will have no idea how to program a solution, because if you think of a simple scenario like identification of face, then as a human being I can identify the face correctly, but to tell an agent to identify a face or to recognize that face is not a easy problem to specify, so which is actually difficult. So we want my agent should learn all those things. So when we talk about this learning, there it can be classified in many ways. So one of the things that you would like to classify here is as inductive learning, which which is a form when 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 the system learns a function, it learns a function from the specific input output pairs. So I'll be given a set of observation, the inputs and the corresponding output. By looking into this set of input output pairs, I would like to find out a general function or a rule so that I can predict it for future observation. Another form of learning is, we call it analytical or deductive learning. So here from a known general rule, we would like to make a new rules that are logically derived. So some form of that stuff we have seen in the predicate logic or in the propositional logic, where we try to deduce some analytical some more information out of the given information. So if we look into the paradigms of learning, so we observe that there are majorly three forms of learning that we will talk about. So these different types of learning are based on the type of feedback that we have. So the basic learning is known as the supervised learning. So what happens here? Here we have the input output pairs. So for every inputs, we have been given the outputs. So the outputs are typically provided by a friendly teacher. So for every input, I know what is the actual output. By looking into this input output pairs, I would like to the learn maybe some function or maybe some rule. So since there is a friendly teacher, so it is known as a supervised learning, because for every input the agent will be guided with some information. Another form of learning is reinforcement learning, where I have some I have some information that I can get, but the thing is the outcome of a action that I am taking is not known immediately. For example, the stuff that we talked about in the planning problem, like we need to acquire bananas, so I can get bananas by stealing the stuff, or I can actually buy the bananas. Now if I steal the bananas, then I have to pay a fine for that, which maybe is not a good way to acquire bananas. But if we buy bananas, then that is the more appropriate action. So so when my agent does an action, so it receives some kind of a evaluation at the end of the actions. So it may happen that immediately you may not get the action, but the action may be observed at a later point of time as well. So the action so with respect to the supervised learning, for every input I get the output immediately. For reinforcement learning, this evaluation that we are talking about may be available after some point of time, so I may not know the outcome of the action immediately. We'll elaborate a little bit more in later slides. The other form of learning is when we do not have any feedback. We call it an unsupervised learning. The agent learns the relationship among its percepts and the trend with time. So, given a set of observation where we do not have any idea, but we would like to classify those observation points, maybe we can proceed for clustering. Or if I have say 100 features based against which I observe certain points, then out all those 100 points may not be important. So I would like to find out the important parameters for for the representation. So identifying the important parameters based on which the observation was made will also fall in a category of unsupervised learning, and which we call the dimensionality reduction. So let us look into more on supervised learning. So in supervised learning, we are given a set of labeled examples. So we have been given this exercise, and we have been given the actual outcome. Now, so this exercise are my input variables, and yi is the actual output variables. So our target is to find out a function f that can map from the given input output pair to the actual output function. So given any combinations of the inputs, I would like to predict the value of y for the given input. So in order to do that, in order to find out that function a, what we like to do that on the given set of examples, you'd like to minimize some error function or the loss function. So what we do here is what we do here so given a set of examples as an observation, so let's say these are my observation example points that I have. So for every pair I for every points I have the xy pair. For every points I have this xy pair. Now I would like to find out a I would like to fit a function f that will map from x to y, and once I find out that function f, then for an unknown input when I have been given some point, then I would try to predict the y value using that f function. So given any other observation, I would like to y for that. Now in order to find out this f function, what we need to do is we need to look for the error that I am making in predicting from x to y on the observed example. So I need to have some measure that how much error I am making while predicting the set of observed points, because I can fit many f function here. Now we have we have to select the best f function. The best f function will be that one which makes very less error in prediction. So I need to have some kind of a error measures when I'm trying to map from this x to y. So important thing, like when I try to predict this value, probably I can say this is a predicted value and this is the original value. So what I would like to do, for every examples on this set, I would like to find out the difference between the predicted one and the actual one. So this error value will guide me, or this error value will tell me how good my f function is. Now if I for some example, so if I go ahead with this kind of a function, like it's simply the difference between these two, then sometimes it can be positive, sometimes it can be negative. So we can make a square of that one. So when we use this as a metric to evaluate how good my f function is, then this is known as the mean square error function, or this is minimization of mean square error value to find out the best f function. So in case of unsupervised learning, where we'll have been given a set of observation based on different parameters, let's say on x-axis I have a parameter p1, on y-axis I have a parameter p2, and we observe this set of points. Maybe it can be something like we have a set of mangoes and we observe the color of the mango, and we observe the hardness of the mango. And Based on that, we observe a set of mangoes, and plot we plot all those observation on a 2D plot, let's say. Now if we observe these plots, maybe what we can actually say that these set of points are very close to each other. Maybe if I have a color which is more towards yellow side and it is less hard, let's say, then probably these are the good mangoes, maybe. And if it's or more towards on the green side, so this is, let's say, more on the yellow side, this is more on the green side, and this is, so this is hard on this part, so hardness decreases on this side. So this maybe it's it maybe it's a green mangoes. So maybe we are not looking for this one. This can be this set of observation may falls into the other category. So we can actually categorize the different set of observation. Like instead of its mango, if we think of this is an observation of the news article based on certain parameters, then we can classify this set of observation belongs to maybe sports, maybe political, maybe entertainment, and so on. So this kind of clustering we can actually do, which is actually known as the unsupervised learning. Because here we have been given the set of observation and nothing has been told, or we are not given any kind of inputs by a friendly teacher. The other form, so this is just an example of that one. So once we have this parameter p1 and p2 based on which we classify, we can actually cluster and we can label each of the cluster with different labels. The other form of learning where we have this reinforcement learning that we talked about a little ago. So here the agent makes a sequence of moves, and the outcome of the moves, all those moves, are known at the end of the episode. So, and the goal is for the agent is to make the move such that the maximum reward that it can actually achieve. So it has to make a moves, or it has to make an action that would maximize its profit or the maximize its return on the reward. So in order to do that, the agent needs to do one of the easy it needs to do a trial and error search, which is one of the basic methodology. And the important point here is that it will have a delayed reward. So typically these reinforcement learnings are used for control applications, or maybe for mostly in the gaming applications, where I make a moves and then I get to observe whether I win or I lose. So the reward for a game, or maybe the outcome of control application, will be known at the end of the episode whether I made a good moves or not. So so I'll so the thing is, the agent will play a number of times based on the outcome of the different episodes. It will gradually learn how to interact with the environment, and eventually it should achieve the goal. so 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 the thing is, agent will interact with the environment. It will observe what kind of returns it is getting. Based on that, it will it will try to choose the best moves. So if it plays a number of times, if it observe the different kinds of returns that it getting for different kind of action that he can make, then out of those observation it can actually learn which could be a good move. So once it learns, it needs to so agent needs to have the idea of state, because the moves that it can make also depends on the states. So it needs to identify the current state, and it needs to decide the action that it needs to decide the action so that it can achieve the maximum reward. So three important aspects for reinforcement learning is the observation, that what what is the outcome from the environment, what actions I am actually making, and what is my goal. So these three are the important aspects for reinforcement learning. in in order to elaborate uh, the difference between reinforcement learning and the supervised learning, because in supervised learning we are provided with the output immediately. So I have the inputs, I have the outputs, and I learn that stuff. But in case of reinforcement learning, I have input, I produce some output, that is the action. The action actually interacts with the environment. From the environment I get some kind of a rewards that is being fed into the learning agent, so that it can take a better action, or it can choose a better action so that it can maximize its rewards. So the the this feedback may not come immediately, so it may come at the end of the episode. So that is the major difference from the supervised learning, where I have the output immediately available for a given input. So here, for the inputs, I do not have the output immediately. So with that background of learning, we will go into learning of trees, or the decision trees. But this is kind of a supervised learning, and this learning is mostly focused to learn boolean functionality. So when I'm saying boolean functionality, it will have only the two outcomes, yes or no. And for a given applications, I can have many such important many factors that can govern the final outcome. So you'd like to find out a very concise representation of those factors, such that if an unknown observation comes to me, I should be able to predict more accurately. So let us take an example that what we would like to do here. So a decision tree is what? A decision tree takes an input takes an input of an object or situation described by a set of properties, and the outputs is a yes or no, which is a kind of a decision that it is trying to make. So the final outcome is 1 or 0. So let's say I uh, let's say we would like to visit a restaurant, and depending on the set of parameters, whether we would like to wait uh, whether we would like to wait in the restaurant or not, that is the question that we need to answer. So whether to wait for a table or not at a given restaurant. So I would like to say yes or no for after observing certain set of factors. So this could be the different parameters, like if I have a suitable alternative restaurant. So if I have a suitable alternative restaurant, then I may not wait, or I can also wait. If the restaurant has a lounge, then I can actually wait, or I may not wait even also. So if it's Friday and Saturday, so maybe on Friday or Saturday I can actually wait, or I may not wait, maybe depending on the other parameter also. My outcome of yes no can also depend whether I am hungry or not, or how many people are there in the group, whether nobody is here, someone is there, or the full everybody is here. Also it depends on the price of the price or the restaurant rating. My decision can also depend on whether it's raining outside or not, whether I made a reservation or not, what kind of food that it serves, and what is the weight estimate. So if it's a very small weight that I need to make, or I need to wait for a very long time. So the outcome of this decision whether to wait for a table or not depends on many factors that we have mentioned here, and there can be many more. So now the question is that given a set of observation where we really waited for some times, and when we have not waited for some time, out of those observations we would like to construct a tree that can answer me, or that can identify the important factor. And if somebody provides me an unknown input, then probably I will be able to predict whether I will wait or I will not wait. So let us look into some of the observations. So let's say we made few observations where we have whether we have alternative or not, whether it's a Friday, and all those parameters that we have looked into the previous slide. And my outcome is either yes or no. So that is the observation that I am making. So given this set of observations, we would like to construct a tree so that we'll be able to answer given any combination. So if somebody gives me, let's say, here yes, maybe no here, yes here, no here, and so on, then what is the outcome for that observation that we would like to do. So for example, we can create a sample tree, or some we just shown here one such tree. So by looking into this tree, like, we have all the parameters: patrons, weight estimate, alternate, hungry, any other alternate, whether it's a Friday or Saturday, whether we made a reservation or lounge, and all those things. Now by looking into this tree, we will be able to answer for an unknown input. Let's say if the patrons are full and my weight estimate is, let's say, 30 to 60. So let's say my patron is full, weight estimate is 30 to 60, and we have no other alternatives, and we have no uh, we have no alternatives, we have made no reservations, and there is a lounge available on the restaurant, then probably I would like to wait for for the restaurant. If we choose another observation, so I would be able to predict that one. For example, if it's full patrons, and let's say my weight estimate is 10 to 30, then probably I will check whether I am hungry or not. Let's say I am hungry, then probably I would like to check for whether I have any alternative uh, any alternative or so. If I have any alternative, let's say yes, then probably I would like to check whether it is raining or not. If it's raining, then probably I would like to wait in the restaurant. So given this observation, like patrons for full, weight estimate for 10 to 30, hungry is yes, I have alternative also yes, and if it's raining, then my outcome is yes. So given any combinations of the inputs, we will be able to traverse from the root of that tree, and we can reach to some conclusions. So now the question is that we can make any such trees. We can create many combinations of the trees, but the question is, what would be a good tree? And also, in order to have a good tree, we need to identify the set of attributes, which attribute we should choose, so that our representation of the tree is the is best or the better, maybe. Or I would like to have a better tree or for representing the all the observation points. So so in order to construct this tree, we will the identifying the base tree is a NP hard problem in terms of computer terminology. So this is a very very computer intensive problem. So therefore we would like to go ahead with some kind of a heuristic or the greedy approach. The greedy approach is very simple. So our idea or our target is to find a small tree consistent with the training examples, because the training example, that means the observation points that we have, we would like to fit those points accurately, because these are the observation that we have made, so we can expect our observations are correct. And for an unknown input, I may predict it wrongly, that's fine, but on the training example, I would like to predict it. I should be able to predict it correctly, because those observation we have already seen, so we have the correct level for those observation points. Now the primary idea for uh, primary idea for constructing the tree is a kind of a recursive loop that we would like to run, and we would like to choose the most significant attribute as the root or the subtree. So whenever I have an option, I would like to choose the most significant attribute for my tree. So the this is the simple stuff. So I need to define, or I need to have some ways using which I should be able to identify the most significant attribute that we are coming to. But before going to that, so the idea is that we pick an attribute, or maybe we can say we can actually specify the most significant attributes that we would like to choose. To split a non-terminal node. So split so so we choose one attribute. When we choose the attribute will split the example into groups, Because let's say if I choose the patrons, the examples that I have seen earlier, if I choose patrons, then some of the examples will fall in this none category, some will fall in the some category, some will fall in the full category. So I will construct these groups. Now for each group we would like to do certain operation. If for a group no example is present, then we would like to return the majority from its parent. So this is just a way to break the tie, or because I do not have any examples for a particular class, so I need to resolve some kind of a tie. And if all the examples fall in the same class, then I can simply return that class. And if it has a mixed exam, so when I say it's the same class, that means all are yes, all are all are either yes or no. So then I return the yes class or the no class. If it is a mixed, like I have some yes class and I have some no class, then I go back to step 1 and I continue that process. So so when so to choose an attribute, we would like to see uh, the how is the split. So the idea is that a good attribute splits the example into subsets that are ideally all positive or all negative. For example, if we choose these patrons with respect to our examples, then we have 12 observations. Actually 6 are yes and 6 are no. So when we choose patrons, some will fall in none category, something will fall in some category, something will fall in the full category. Now if you look into this none, then all falls into the no class. When it is some, all fall into the yes class. And when it is full, something is yes, something is no. So this is one of the observation. And let's say we choose type as an attribute to split the examples. So when we have this type, what we observe, that if it can falls into the French category, both yes and no, Italian yes and no, Thai yes and no, and fast food or the burger yes and no. Now now the thing is, if I split with patrons, then for certain observations we can readily classify here, because if it falls in none, then we are very sure that it will go into no. If it's some, then definitely it will go into yes. But if we select to split the examples based on the type, then we are unable to say that whether the examples fall into yes category or the no category directly, because we need to explore for some other attributes. Because if I have these observations, then we cannot actually specify uh, whether my outcome will be yes or no. But in this scenario, when I have these patrons, at least for some examples, I can readily conclude that what will be my outcome. So definitely my patrons is a best attribute to choose in this example. So to choose best attribute, there is a information theoretic um, measurement that we would like to explain now. So let's say I have three buckets. In one of the bucket I have four red balls. In another bucket I have three red balls and one blue balls. In another bucket I have two red balls and two blue balls. So if I have this information, now if somebody asks something like this, how much information do we have on the color of a ball drawn at random? So in the first bucket, what we can say, that the ball will be red. Whatever ball I can draw, it will be red always for the bucket 1. For the second bucket, I can say it will be with 75% certainty that it will be red. For the third bucket, with 50% certainty, it will be red. So for bucket 1, it has the maximum amount of knowledge about the color of the ball, because whatever ball I draw from here, it will be red always. So we have the maximum knowledge about the bucket 1. And we would like to define another term which is known as entropy, which is the opposite of the knowledge, or which is kind of a measurement of the disorder. So here, since it has the bucket 1 has the maximum knowledge, so and entropy is the opposite of the knowledge, so bucket 1 has the least amount of entropy and bucket 3 has the highest entropy. And we say entropy is less when there is a less disorder, and entropy is more when there is a high disorder among the system. So we'll explain what does that disorder, what does that mean. So would like to continue with the same example. So we have these three buckets that we talked about in the previous slide. So now we would like to ask this question: how many distinct arrangements of the balls are possible? So when we have this bucket 1, there is only one possibility. For bucket 2, we have 4 possibilities, and for bucket 3, we have 6 possibilities in which we can actually arrange the ball. so the thing is, the situation is something like this. So let's say I have these 3 buckets and I have this sequence of balls where I have all red, we have 3 followed by 1 blue, or we have 2 red followed by 2 blue balls. Now now the thing is, if I draw one ball from a bucket and I replace that ball with the same ball once again, so I keep on drawing one ball with replacement. Now my target is to find out the the specific sequence in which the balls are arranged in the different buckets. so the thing is if I draw a ball from bucket 1, I will always get a red. So effectively I will be able to reproduce the whole sequence by drawing 4 balls, because I have only one arrangement of the balls. In case of bucket 2 I can reproduce this sequence of balls, but there can be other sequence as well. Like this is the sequence that I would like to find out, but there can be other sequence also which may come up when I'm experimenting, when I'm drawing one ball from that bucket. Similarly for bucket 3, the sequence that I'm looking for is this one, and but it may turns up, it may lead to other kind of observations as well. So in order to, if I want to find out the same sequence as given in the bucket, then for the first bucket I will be able to reproduce as it is, but and it will be least in case of bucket 3. So what we can say, the disorder with respect to bucket 3 is more, and disorder about the balls in bucket 1 is less. So the probability of finding a specific arrangement in four draws of balls is less for third bucket because the number of possible arrangement is larger. So that is the situation. So what we would like to say, that this has the maximum entropy, this has the least entropy. So let us take an example. So let's say we are given those three buckets, uh, and we are given three buckets, and we would like, and the rules are as follows. We choose one of the three buckets, and we are playing a game with this set of rules. We choose one of the three buckets. We are shown the balls in the buckets in some order. Then the balls go back in the bucket. So basically we are given the sequence in which the balls are present in the bucket. We then pick one ball out of the bucket and we record the color and then return the ball back on the bucket. Fine. Now if the colors recorded make the same sequence, that the sequence of the balls we are shown at the beginning, then we win, and if not, we actually lose. So so now the thing is, which bucket we should choose. So we can actually calculate the probability of win for bucket 1, for bucket 2 and bucket 3, and based on that outcome we can actually decide which bucket to choose. So if we choose bucket 1, then I can actually win if the balls that I'm drawing from the bucket has this sequence, because in the first bucket I need, if I need to win, then I need to have a sequence like R, and the probability will be getting an R is 1 here, getting the next R will be also 1 because we replace and all events are independent. So effectively I get a value of 1. Now for bucket 2, if we need to win, then I need to have a sequence RRRB, and the probability of win for bucket 2 will be something like 0.75 times 0.75, because getting a red ball has 3/4 probability and getting a blue ball has 1/4 probability. So you can find out this value. For bucket 3, if you would like to win, then I need to have a sequence RR BB, and the probability of win for bucket 3 will be getting a red ball. Here will be 0.5, and for all the observation it will be 0.5 because it's a balanced distribution. So so if we look into these observations, then definitely we can say the bucket 1 is the best to choose because it has the highest probability, but bucket 3 has the least probability, and so the entropy for bucket 1 is less and entropy for the other bucket is more than the bucket 1. So when we have a when we can have disorder, then we say the entropy is high, and when there is a less disorder, then we say the entropy is less. Now, so one thing to note. So in order to find out the best possible bucket, we measure the probabilities. Let's say we have 100 balls here, then for this probability, so it will be multiplication of a value which are less than 1 in most of the situation, because this is a very rare case where the probability will be 1 always. So it will be product of values which are less than 1. So if I need to multiply 100 of those, the value will be close to 0. So in order to overcome that issue, we would like to have a different measure. So products of many probability terms will make the metric very small and create precision problems. So instead of having the probability as it is, we can consider the logarithm of the probability, so which will convert the product into a sum, and since the probability terms are fractional, the logarithm will be negative, and so we can take a negation of the actual value. So effectively for bucket 2, if you would like to compute, then we get logarithm of the probability will be something like this, and the value will be this much, and we have 4 observations. So we would like to take the average in order to normalize these values. So effectively this is the same, and this we divide by 1/4 because we have 4 observations, and this will be treated as my entropy, is the measure of disorder. So the point to note here, like for bucket 1 the probability is 1, so the entropy will be 0. For bucket 2 its entropy will be more. So in order to clarify, in order to make a concrete expression, so the entropy will be estimated with an expression something like this, where this m you can think of is the positive example, number of positive examples, and n is the negative examples that we have in the observations. So this is the probability of having a positive value. This is the negative examples that we have, and when we take the average, this factor will actually come. So for example, when we took about the bucket 1, all the examples fall in the yes category, and that is the observation. So the entropy for bucket 1 will be 0. So entropy for bucket 2 will be this much that we have seen. So this value is nothing but 0.75. so if you look into these three values, then I can represent as -3/4 log of 0.75. So this stuff is represented here. Similarly for the blue balls, and this is the observation. For bucket 3 again we can continue in that way, and we observe the entropy is 1. So now coming to attribute selections for the problem. So we would like to measure the information content or the entropy. So when we choose one of the attributes, it may divide the example into several classes, and the information content based on that attribute will be defined in this manner. So the same as the entropy that we have just seen. So it's some probability times log of some that probability. So we would like to measure the information based on that entropy values, and we would like to sum over all the classes. So for a training set containing p positive example and n negative examples, the information content that we can measure through this expression, so which is same as our this one. So it's a kind of a measure of an entropy. Now we choose an attribute. If we choose an attribute A and it divides the training examples into, let's say, v number of classes, and in each of those classes I have, in each classes, let's say in E1 I have P1 in the positive class, N1 in the negative class, and so on and so forth. Now once we choose an attribute A to partition all those examples, then we can actually measure the we can actually measure the remaining disorder based on these attributes, which we can actually measure the entropy after the partitioning based on the attribute A. Because if we choose attribute A, it will, so I have a set of examples, I have some observations here, and based on that attribute A, some will fall in this class, some will fall in that class, some will fall in that class. So by looking into this stuff, we would like to measure how much is the entropy at this level. So what is the remaining stuff or the remaining disorder that are available once we partition with that attribute. So the information gain that you would like to measure, or the reduction in entropy, will be the original information and is the difference and the remaining stuff. So this part corresponds to this one, and remainder A corresponds to this one. So I have the original examples here. So I know the information content at that level, because among these examples some are positive, some are negative. And once we partition based on attribute A, I observe this thing, and I can actually measure the entropy for that observation, which is the remainder A, that we can compute using this expression. Now I would like to find out the information gain. So if I choose if I choose attribute A, then how much information I am gaining out of that stuff, or or what is the reduction in the entropy that I have. Now I would choose, so when I have this situation, so I can have many different attributes. I can have attributes A, or I can have attributes B, or so on. Now for each of those attributes I would like to measure this information gain, and finally I will choose that attribute that has the largest information gain. So that we will use in our algorithm to choose the most significant attributes. So let us look into our examples. So in our training examples we have 6 positive examples, 6 negative examples. So the information content for the original stuff is just 1 bit. Now when we choose patrons as my attributes to classify the examples, then we get an information gain of this much. So this is because, so this part corresponds to this part corresponds to this corresponds to the example where it falls in the none category. So this one falls to none, this one falls to some, and this one is for full. So I have 0 positive example and only the negative examples. And so this is the so I have only the negative examples, I have only the positive examples, sorry, I have only the negative example here I have only the positive examples. So therefore it is 1. I do not have any the opposite examples. In this case I have 2 in the positive part, 4 in the negative part. So the information gain when I partition the example with respect to patrons, we observe this, and if we partition with respect to type, then my information gain is 0, because if we partition with respect to type, we cannot actually classify anything, because all the classes will have the equal observation of positive and negative examples. So we need to look for another attribute based on which we can actually classify. so patrons will be selected for the classification, or for the most significant attribute. So you have to consider for the other attributes also, but we have just shown only for 2, because you have to repeat the same process. So if we continue to do so, we get a decision tree something like this. So initially we have this we choose the patrons, we find the most significant attributes which has 6 negative and 6 positive examples, and when we choose, so we based on these patrons we observe 2 negative examples, 4 positive examples, and we have this mixed scenario. Now when we have only one class, I can actually label that stuff immediately, so which is being happened here. So if you remember, in the algorithm we talked about that based on the attributes we classify, and then for each of the classes we try to label. We can label only for that class when all the examples fall in the same category, either yes or no. So here every example falls in the no category, so we can actually label this class as no, in this class as yes. But for this scenario we cannot label anything here, so we have to look again, we have to look for another attributes, and this again is nothing but doing the same steps that we have done at this level. So again we have to choose the most significant attributes, and out of those available attributes we found that it's hungry, let's say. So it classify the set of examples 2 in the no category, so we can actually classify this one, and remaining 4 falls in here. So again we have to repeat the same process, we have to find out a significant attribute. So here let's say we find the type is the most significant attribute among the available attributes at this level. So this classify these 4 example in this manner. So 0 fall in the French category, 1 fall in the Italian, 1 positive and 1 negative example in the Thai, and 1 for the burger or the fast food. Now for this case we know it will be labeled with no, for this case it will be labeled with yes, because there is only one example, or example falls into only in the one class. In this case we do not have any examples, so we assign as the parent class. Parent class again we do not have any type, so we can choose any one of them just to break the ties. So here we have chosen as yes. We could have chosen no as well, so but here we have chosen yes. Now on this part we have one no and one yes, so we have to look for a situation. We need to look for another attributes, so we choose Friday or Saturday, and we observe that one no example here, one yes example here, so we can actually label with no and we can label with yes. Now it may happen that we have some attributes based on which, so let's say I have some attribute A, and based on which we have some classification, let's say say 2n, and for this one let's say I have 4n and say 3 yes. Now in this situation, so I can label this as no, there is no issue with that, but for this case I cannot label anything, so I need to look for other attributes in order to split those example. It may happen that I do not have any more attributes to classify these examples. Then what I can do in order to resolve this situation, we can treat as no because it has more number of no example. So by looking into the maximum examples, we can select to label that node as in that class. And if both of them have the equal stuff, we can choose one of them as an just to resolve the ties. So now the question is, what is a good tree? So for a good tree, it should not be a very small, and it should not be also a very big, because if it's small, then it may not handle all the important points, because it needs to handle the important, but possibly the subtle distinction in the data. So it needs to handle the important factor. But if we try to have so many factors, then it can actually lead to some kind of a inefficiency, and it can lead to a situation called the overfitting of the examples. Like for example, if I throw a dice, and my question is whether 6 will appear or not. Now if I have an attribute like the weight of the dice, if I have the color of the dice, and many other irrelevant parameters, and if we observe all those examples, then it may happen that if the weight of the dice is, let's say, 10 grams and the color is blue, then then 6 can actually turn up. So that kind of conclusion that we can actually end up with, so which is actually not true, because the appearing of 6 should be independent of the weight when I am assuming it's a fair die, and it will be independent of the color of the dice as well. So so those kind of overfitting situation can actually appear, so we need to avoid that stuff. With so before I finish, I would like to add one more thing here. So when I obtain this final decision tree as this, we can actually construct the boolean functionality out of this stuff. So this tree can be expressed as an outcome yes. So whether I will wait or not, that that will be that I can answer from this tree. So I can construct a boolean expression something like this. So whether I will wait or not, and my outcome for yes, I can specify in this way. So my outcome will be yes if my patrons is has sum, or or patron is full, logical ended with I have to check for hungry. Yes, if I am hungry, yes, then I have to check for the type. So type French, that can give me yes value, or I can have hungry yes, because this, and type, let me put logical or here, hungry yes, type is Thai, or let me write is for the burger, logical or, and I am hungry yes, and it's Friday or Saturday yes. Friday, uh, sorry, I made a mistake here. So it will be Thai and Friday or Saturday. Yes. So this is the actual Boolean expression to predict. Yes. So I can actually construct a Boolean expression out of this stuff. So with this, uh, I will give you an exercise problem where I have to predict. So this is an example where I decide whether I will play tennis or not depending on the outlook, temperature, humidity, and wind. So you have to construct a decision tree out of this stuff. You have to select the most significant attributes, and then you have to construct the whole tree. Whatever we have done for the this example, you have to do for this example. So with this, I would like to stop here. Thank you.